Hello, today we're going to work on adding up a geometric series. And we're going to use this formula here. And after several examples, we will take a look at so-called infinite geometric series. This is the formula for the finite examples. And hopefully we'll have time at the end of the video to show you the algebra behind this formula, how to derive it for yourself. Let's get started. Well, this is not a series at all. This is a sequence. But if you insert plus signs between those terms, you'll find that you have a finite geometric series. What makes it geometric is that when you divide two consecutive terms, like the 12 divided by the 2, you consistently get the same answer. 12 divided by 2 is 6, 72 divided by 12 is 6, 432 divided by 72 is indeed 6. So that's called the common ratio, and it's the R that you see up here in this formula. You'll need to know what the first term is. That's the easy part. That's 2. And that's the A that you see in this formula. And then you'll also need to know how many terms you have, and in some cases you can just count them up. There's 1, 2, 3, 4 terms. Now, what I'm going to do is try to rewrite this using the common ratio, and I'm going to put some plus signs in there to make it a series. So if I use 6 as a common ratio, it doesn't appear in the first term, but the second term is 2 times 6. And the third term is 2 times 36, but 36 is the second power of 2. Last but not least, I have 2 times, it turns out that this is 2 times 6 times 6 times 6, 2 times 6 to the third power. And now this looks like the model, right? Now notice that there's still 4 terms, 1, 2, 3, 4 terms, but the highest exponent you end up seeing is a 3. Okay, we want to identify A and R and K so we can use this formula. Let's start off easy. A is equal to 2, it's the first term. R is the common ratio, we mentioned it was 6. K is the number of terms. Sometimes you have to look here to figure out what K is. You would actually take this 3 and add 1 to it. But in this case, I can just count 1, 2, 3, 4 terms. And so the answer to this finite addition problem can be computed like what we see here. So that's A times this fraction. 1 minus 6 on the bottom, and 1 minus 6 to the 4th power. See, the exponent that goes here is equivalent to how many terms you have there. Okay, and to save time, I ran this through a calculator, and I got 518 for it, or you can try to figure it out in your head. But we're going to move on. Let's do another example here. Let's take a look at problem 4 on this exercise. It says 10 plus 30 plus 90 plus 270 plus 7,290, and then you see a dot, dot, dot there. There must be some missing terms. Well, I always start by trying to figure out, is this geometric? From what I can see, 30 divided by 10 is 3, 90 divided by 30 is 3, 270 divided by 90 is 3. Yeah, the common ratio is 3. So just like with the last problem, let's start off by writing each term as 10 times some power of 3. 10 times 3 is 30. 10 times 9 is 90, but of course 9 is 3 squared. 270 is 10 times 27, but 27 is 3 to the third power. So then you're going to want to figure out down here at the end what power of 6 multiplied by 10 is going to get you 729. And the answer is, it ends up being 10 times 3 to the 6th power. Okay, now I think you know everything you need to know to use this formula up here. In particular, the first term is 10. That's A. Common ratio is 3. Number of terms. Oh, we didn't figure that out yet. How many terms are there? Well, I'm not sure you can just go in here and count terms because you've got these missing terms here. But remember, that highest exponent that you see on r added by 1 gives you the number of terms. So in this problem, k equals 7. So we want to use this formula. Now we do it like this. First term times this fraction. On the bottom, it's 1 minus the common ratio. And in the numerator, it's 1 minus the common ratio, raised to the number of terms. And I have worked this out previously to come up with 10,930. Okay. There are exercises on this page that are written in sigma notation. So we're going to take a look at problem 8, and I'm going to try to write out the terms. If you haven't seen this before, it's not as bad as it looks. The idea is for n equals 0 and 1 and 2 and 3 and 4, that's 5 different n values. You're going to write this out. Start with n equals 0. Okay? 0.25 to the 0 power is 1 times 512 is just 512. Next, we have 512 again, but this time you're going to multiply by this, which is negative 1/4, to the first power. Because remember, the indices go n equals 0, n equals 1, n equals 2, all the way up to 4. So this is times negative 1/4 to the first. You'll do it again to the second, and you got to carry all the way out until you get to a 4th power. But to save time, I'm not going to write them all down. So written out like that, and we go back up to what the formula said up here, it's pretty easy to get the a and the r and the k that we need. What's the a? A is 512, the first term. What's the r? The common ratio is negative 1/4, which I think you can see would make this series alternate. You go from a positive 512 to a negative number here, to a positive number here, because squaring negative 1/4 makes positive. So this is alternating finite geometric series. First term 512, common ratio negative 1/4, and how many terms? It's not 1, 2, 3, 4 terms. Remember, there's missing terms here. So in this case, you either have to write them all out, or you have to go to that highest exponent and add 1. So there's 5 terms. Okay. So this series should add up to 512 multiplied by this ratio, where I do 1 minus, 1 minus negative 1/4 on the bottom. That's 1 minus r. And on the top, I also do 1 minus the common ratio. But I raise it to the 5th power. Okay? And if you wanted to do all this in your head, have fun. This is a negative, because the odd power of negative is negative. And this is positive, because minus a negative is positive. So the top of this would look like 1 plus, and this ends up being 1 over 1,024. This ends up being 1 plus 1/4. If you enjoy that kind of thing, go for it. I've previously worked this one out to come out to 410. All right. Now let's turn our attention to infinite examples. Infinite geometric series. Boy, are these important. There's a formula. It's kind of nice. It's even cleaner or easier to use than the previous formula. Let's take a look at what you do. You just put the first term on top and divide by 1 minus r. But there's an important condition that has to be met. The r value has to be strictly between negative 1 and 1. If it's not, this formula won't work. So it's easy to use and it works well. but you have to satisfy the conditions. There's two conditions actually. One, make sure you have geometric series, and two, make sure you have an r that's close enough to 0. So let's take a look at two examples where you can't use this formula to start with. This is not geometric. 2 divided by 1 is 2, but 3 divided by 2 is only 1.5, and 4 divided by 3 is 1.333. You get the idea. There's no common ratio, and so this is not geometric, so we won't be able to use this formula. And again, the dot, dot, dot means just keep adding, so the next term is 6 plus 7 plus 8. It should be pretty clear that this adds up to an unbounded pile of add-ins. They add up to infinity. This one also adds up to infinity. Why? Well, all these numbers are bigger than 1. And of course, if you did 1 plus 1 plus 1 plus 1 and you never stopped, you could make that answer as large as anybody in the room requested. You could make it arbitrarily large. I will point out that this is geometric, though, because 2 divided by 1 is 2, and 4 divided by 2 is 2, and 8 divided by 4 is 2. But still, you won't be able to use this formula. All right, let's take a look at an example where we can use that formula. This one, for example, it's geometric. A half divided by 1 is a half. But, no, excuse me, not this one. This one. A half divided by 1 is a half. A fourth divided by a half is a half. An eighth divided by a fourth is a half. The common ratio is a half. Or another way to think of it is you could multiply this by a half and get the next term. 1/8 times a half is a 16th. Well, now that we've established that, we've got the two numbers that we need for this formula. Okay? We need to know the first term, and we need to know the common ratio. And then all we do is plug into that. So this adds up to the first term divided by 1 minus the common ratio, and this adds up to 2. And it's pretty easy to convince yourself that this is right. Picture a number line where you start at 1 and you add a half. Okay, now you're halfway between 1 and 2. Now add a fourth to what you just had. You're at 1 3/4, and that's halfway between 1 1/2 and 2. Now add an eighth. You are halfway between 1 3/4 and 2. So you just keep closing the gap, or cutting the gap in half, and you can get arbitrarily close to 2. All right. Here's another geometric series that uses 1/2 as a common ratio. And it's going to add up to 256, and I'll let you work out the details on that. Okay, this one is we're not going to do. It's not geometric. It's famous. It's called the harmonic series. But you can check quickly and find out that a half divided by 1, which is a half, is not what you get when you do a third divided by a half. You get 2/3, and a fourth divided by a third is 3/4, etc. It's not geometric. Look this one up to find out that it adds up to infinity also, which is astonishing. How about this one? Is this geometric? It is. -1 divided by 1 is -1. 1 divided by -1 is -1. -1 divided by 1 is -1, etc. Divide any two consecutive terms, you get -1 for an answer. So that's a geometric series. And you can have all kinds of fun with this if you make the mistake of assuming that it has an answer. This one doesn't go to infinity, but it doesn't really have an answer, like 2. This one does what we call diverges. It diverges by oscillation. And shouldn't be too surprised because there's an important condition up here that's not met. -1, the common ratio, is not close enough to 0. We have to be strictly between -1 and +1, and this is just a little too far to the left. Okay, we're going to do one more problem here. And we'll do problem 9. It's given to us in summation notation. Let's one more time practice how to write out a series that's given to us in summation notation. Take n equals 0 and put it up here. Any non-zero number raised to the 0 power is 1 times 512 is going to be 512. Now next, we want to take 512 and multiply it by the n equals 1. So the first power. And then we advance the index again from 0 to 1 to 2. And we're going to go 512 times negative 1/4 to the second power, etc. Do we know the two things that we need to know to write this down? Yeah, we know the first term is 512. And we know the r value is negative 1/4. So we write that out. We get 512 divided by 1 1/4, or 5/4, which comes out to 2048 over 5. Okay, I promised you we'd look at the algebra behind the formula on the first page, which looks like this. How in the heck do you manipulate this to look like that? That's just a few steps, and I haven't gone 20 minutes yet, so I think we'll take a look at the algebra now. Okay. Let's start off with a plus ar squared plus until you have a times r to the k minus 1. And you just set that equal to, well, for now we'll call it s. We're going to try to show you that s equals that formula that we just looked at. Multiply both sides by r. The right side now looks like r times s. And the left side looks like all of these multiplied by r will give you an r here where you didn't have one. Give you an r squared here where previously you had just r. In other words, all these powers of r go up by 1, including this one. So if you multiply this by r, I'll do this over on the side here, a times r to the k minus 1 times r is, put a 1 here, and add these exponents together. K minus 1 plus 1 is just k. Now, I also might mention that the term that comes right before this looks like that, because it's one lower. Whenever you look to the left, you get terms that are 1 power lower of r. So if this has a k power, the term right before it looked like this. Now, when you look at this, it looks almost exactly like what we started with up here. But there's something missing. Yeah, we're missing the a. So I hope it makes sense to you that I can pull all these terms out and replace them with s decreased by a. And then I still have this term. And we have 2 or 3 more steps and we'll be done. Subtract this from both sides. Actually, no, subtract this s from both sides like this. Because we want s's all on one side. So now the right side looks like rs minus s, and the left side looks like negative a plus a times r to the k. I'm going to write this term first, and the minus a second. And then we just have a little factoring to do here. Factor a out of these, you get r to the k minus 1, and factor s out of these, and you get r minus 1. Divide both sides by r minus 1, and now it looks like this on the left. Oops, looks like this on the left. I'll clean that up in a minute. And divide by r minus 1. Okay, see, I'm dividing both sides by r minus 1. And I'm doing that to cancel all of that. So now on the right side I just have s. And apologize for the error there, but I'm going to move the s to the left, and I'm going to move all these to the right so that it looks exactly like it did when we saw it for the first time. I'm also going to multiply both these by negative 1. You don't have to, but so that both of these subtractions look reversed. So this becomes 1 minus r to the k, and this becomes 1 minus r. And that's the end. Well, I hope you learned something today. And if you're one of my students, enjoy the remainder of that geometric series worksheet. Goodbye.